In today's lecture, we shall study how to obtain state space representation from differential equations and how to obtain state space representation from transfer functions. So let's first talk about state space equations from differential equations. So here is a general nth order differential equation which describes a mathematical model of some physical process, and we want to obtain state space representation for this particular system. Here this equation, what is y dot? Y dot is derivative of this variable y with respect to time, and here there will be second derivative, third derivative, and this is n minus first derivative of this variable y. This is the nth derivative of y. So the procedure to obtain state space representation from this differential equation, that is very simple. We define some state variables. For example, this variable y is named as a new variable x1. We have given this a new name x1. And likewise, this derivative of y with respect to time, that is given another name x2, and similarly the n minus first derivative of y, that is given the name xn. And then what is x1 dot? The derivative of x1 with respect to time, that x1 dot is equal to y dot, and from this equation what we see is that y dot is equal to x2. Therefore x1 dot is equal to x2. Likewise, what will be x2 dot? X2 dot will be equal to y double dot, and which is given a new name x3. So x2 dot is equal to x3, and so on up to n minus 1, xn minus 1 dot, that will be equal to xn. And xn dot, what will be xn dot? From here the derivative of xn, that will be equal to nth derivative of y, and from this equation nth derivative of y, an expression for this nth derivative can be easily obtained. Shift all these terms to the right hand side. So that is done over here. Xn dot, that is equal to this input u, which is written over here, and then this term brought to the right hand side, what will be that? A1 with negative sign minus A1, and the n minus first derivative of y, n minus first derivative of y, that is given this name xn. So A1 xn minus A1 xn is this term. Likewise all other terms, and this an y, that is minus an x1, because y is named as x1. So what we have done is that this was an nth order differential equation which described mathematical model of some physical process. We have converted it into n first order differential equations, and these n first order differential equations, we know that these are called state equations, and these variables x1 up to xn, these are called state variables. So these first order differential equations, these also describe the mathematical model of the same physical process. We can also write these equations in matrix form, that is written over here. We have simply written these equations in matrix form over here. For example, this first equation, x1 dot is equal to x2, that is written over here. x1 dot is equal to 1 multiplied by x2 plus 0 multiplied by u, and likewise all other equations. The last equation is also written over here. Likewise the output equation, this y, that can also be written in terms of newly defined state variables. We know that y is equal to x1, and that is written over here. Y is equal to 1 multiplied by x1, and this is our standard state space representation of this system. So the procedure to convert a differential equation into state equations That is very simple. We define new state variables and write the first order differential equations. Let's elaborate it with the help of a simple example. Here we have this simple system. Mathematical model for this system can be easily obtained. We have already studied the approaches. We can simply write the force balance equations. There are multiple forces acting on it. This is an external force applied to this mass, and there is a force due to this spring, force due to friction, force due to this inertia. And writing the force balance equations, as we studied earlier, we have this mathematical model. So this differential equation describes the mathematical model of this physical process, and we want to obtain state space representation for this system. The same differential equation can also be rearranged to write in this particular format. We have simply divided the entire equation with this m. And now the procedure to convert it into state equations is very simple. We define state variables. Let's define x1 to be equal to y and x2 to be equal to y dot. What is meaning of this symbol? This means that we have defined it in this way. We have named this y to be equal to x1. Likewise, we have named y dot to be equal to x2. And with these definitions, x1 dot is obviously equal to x2. X1 dot will be equal to y dot, and y dot is equal to x2. So x1 dot is equal to x2. And what will be x2 dot? X2 dot will be equal to y double dot, and y double dot, an expression for y double dot can be easily obtained from this equation. Y double dot will be equal to 1 by m multiplied by u, that is written over here, minus this term brought to the right hand side will be minus k over m multiplied by y, and this y have given we have given it another name, that is equal to x1. So that term is written over here, minus k over m x1, and likewise this term minus b over m, and this is named as x2, that is written over here. So this is state space, these are state equations, and these can be written in matrix form. That is easy, everyone among you can do that. And this is the output equation, y is equal to x1. So that is the procedure to obtain state space representation from differential equations. That is straightforward, we can easily do that. Any question from this discussion? So everything is very simple. Similarly, we can also obtain state space representation from transfer functions. We have extensively studied how to describe mathematical model of physical processes using transfer functions, and now these transfer functions can also be converted into state space models. The procedure is again simple. From the transfer function, we obtain differential equations, and once we have a differential equation, then obtaining a state space model is simple, as we did on previous slide. So how to obtain differential equations from transfer functions? That is also simple. Let's elaborate it with the help of some simple system. Here we have a transfer function, and we want to obtain state space representation of this physical process, this system. And first we need to convert it into differential equation. For that purpose, we rewrite it in this form. We have simply multiplied this denominator with c of s, and r of s is brought to this right hand side, that is given over here. So this s is basically this is typo, this is small s, the Laplace variable s. So what is s multiplied by c of s in time domain? What is that? Right, time derivative of c with time derivative of c, that is s multiplied by c of s. Likewise, s square multiplied by c of s is c double dot, the second derivative of c with respect to time, and s cube multiplied by c of s is the third derivative of c with respect to time. So we can easily write the corresponding differential equation that is given over here, and once we have this differential equation, then the state equations and state space description can be easily obtained as we have done on previous slides. That is, we define new variables and write the first order differential equations. So for example, C can be defined to be equal to x1. Then what will be C dot? C dot will be equal to x1 dot, and we give it another name that is equal to x2. Likewise, C double dot will be equal to x2 dot. C dot is x2, so C double dot will be equal to x2 dot, that is written over here, and we give it another name x3. And what will be x3 dot? X3 dot is equal to the third derivative of C with respect to time, and this third derivative of C with respect to time can be easily read from over here, that is equal to minus 24C this term, minus 26C dot this term, and likewise the other terms. And now this C we have defined it to be equal to x1, C dot we have given it another name x2, and C double dot we have given it another name x3. So we write this equation in terms of newly defined variables, and that is given over here. So we have converted transfer function into differential equation, and then this third order differential equation is now converted into three first order differential equations. Here is the first differential equation, x1 dot is equal to x2, x2 dot is equal to x3, and x3 dot is given by this expression. So we have these three first order differential equations, which can also be written in matrix form, that you all know how to write it in matrix form. And likewise, what about the output equation? We generally denote the output with y. So y is equal to C, and C is equal to x1. So therefore y is equal to x1 from this equation. So this is state space representation of this transfer function. Here we make one observation. This matrix, this system matrix, has some special structure. That is, here 1 and here is 1, all other entries are 0, and in the last row of this matrix, what are these things? These are basically, you see that these are the same coefficients written in reverse order with a negative sign. So minus 9 this coefficient, minus 26 this one, minus 24 this one. So all these coefficients are written over here with negative sign and in reverse order. So for obtaining state space representation from transfer function, we can simply apply this shortcut as well without going into all these details. What we can do is that we can write this matrix in this spatial structure, and last row of this matrix are the coefficients of this denominator polynomial written in reverse order with negative sign. So you can simply use this shortcut to write the state space representation of this transfer function. So is this clear? Any question up to this point? No question? You can also utilize MATLAB to obtain, to convert a transfer function into state space. This command TF to SS that converts the transfer function into state space. This command needs two arguments, the numerator polynomial and the denominator polynomial, and it returns these four matrices: the system matrix A, input matrix B, the output matrix C, and feed forward matrix D. This command, you are well familiar with this command TF. This can be utilized to enter a transfer function into MATLAB. We can also sometimes it is convenient to represent these state equations in terms of block diagrams. That can also be very easily done. This is the state space representation of this transfer function, as we did on a previous slide. So we can represent these state equations in terms of this block diagram. How we obtain this block diagram? So if we look at this variable x1, so what will be this signal? If this signal is x1 dot, then this is the sign of integral. So if this signal is x1 dot, then this will be x1. The integral of x1 dot will be equal to x1. So x1 dot is the same as x2. That means that this block over here, basically it implements this first differential equation, this one, x1 dot is equal to x2. This signal over here is x1 dot. If this is x1, this is x1 dot, and x1 dot is equal to x2. So this equation is implemented over here. Likewise, this signal is x2, and what will be this signal? X2 dot. X2 dot is equal to x3. This equation is implemented over here, and this signal is x3. So this signal will be x3 dot, and what is x3 dot equals to? X3 dot is given by this here. This 3 is this subscript 3 is missing. So basically this is x3 dot. X3 dot is given by this expression, that is 24 multiplied by the reference signal, 24 multiplied by this signal, and then minus 9x3. This signal is x3 multiplied by 9 and then multiplied with negative sign, minus 26x2. So x2 multiplied by 26 and multiplied by this negative sign. Likewise, minus 24x1, 24 x1 with negative sign over here, and this y is simply equal to x1. This signal is x1, and we also have given this the name y. So we can easily obtain block diagrams for these state equations as well. These block diagrams will be these are sometimes useful, and that is why we are also introducing these things. So is there any question? So we have learned how to convert a transfer function into state equations. However, this particular transfer function, there was no polynomial in the numerator, that is, there was no finite zero in this particular transfer function. What will be the procedure to obtain state equations if the numerator also involves some polynomial? That is, if there are some finite zeros in the transfer function as well, then how we can obtain state equations? Again, the procedure is demonstrated with this simple example. What we can do is that we can split this block diagram into two parts. One part is over here, that only involves the denominator polynomial, and the second part is over here, which contains the numerator polynomial. So you see that basically this block diagram and this thing, these are equivalent. We have only split this transfer function into two parts, the part which contains the denominator polynomial only, and the part which contains numerator polynomial only. For this first part of this block diagram, we have already learned how to obtain state space representation. That is simple. We shall convert it into differential equation and then convert it into first order differential equations. That will be state equations. And we have already studied a shortcut as well. We can simply write these coefficients over here in reverse order with negative sign. Basically, we have already done it on previous slide. The only difference is that over there, here it was, I think, 24, and here is 1. So that is why in the input matrix on the previous slide it was 24 over here, and here it is 1. So for this part, obtaining the state space representation is simple. What about this thing? How to handle this thing? So this equation is written over here. This signal C hat was intermediately defined. So this actual output C, that is equal to C hat multiplied by this this expression over here. And we can also note that this C hat, what is C hat basically? If you look, if you see at the previous slide, this output was basically equal to the state variable x1. So here the only difference is that this is denoted by C hat. So C hat is equal to x1. You can go back to the previous slide and see that this is actually x1. And now this s multiplied by x1, what is that? x1 dot. Likewise s square multiplied by x1, that is equal to x double dot in time domain. That is written over here, the same equation written in time domain. And furthermore, what we see is that x1 dot is basically equal to x2. That is x1 dot is equal to 1 multiplied by x2. So this x1 dot is equal to x2. Likewise x1 double dot, which is equal to x2 dot, x2 dot is equal to x3. So writing this equation in terms of these state variables, we have this output equation, and that equation written in matrix form is over here. So if the transfer function involves some finite zeros as well, again we can very easily convert it into state space. The procedure is simple. We split it into two parts. This part which only contains the denominator polynomial and the part which contains the numerator polynomial. For this part, we can easily obtain the state space representation, this spatial structure of this matrix, and the coefficients of this denominator polynomial written in reverse order with negative sign. And what about the output equation? This output equation is changed. So here we have, again you see that the same coefficients 2, 7 and 1 written in reverse order. So this is how we can convert transfer functions into state equations. So any question up to this point? Is it clear? We can also obtain block diagram representation of these state equations. It is the same as we did for in the previous slides. The only difference is the output equation. These state equations can be easily represented with block diagram. The only difference over here is the output equation. So here is the block diagram representation of these state equations and the output equation. Basically, this part over here, this is the same as for the previous example. We have implemented these state equations, and the implementation of the output equation is over here. This output, that is equal to 2 multiplied by x1, 7 multiplied by x2, and 1 multiplied by x3, and then all these signals added to get the output. So is there any question from this discussion? In the next lecture we shall learn how to convert state space representation into transfer functions. In today's lecture we learned how to convert transfer functions into state equations, and in the next lecture we shall study how to convert state equations into the transfer functions.